So I was really amused this morning to hear Philip Candelas' answer to the question, why are we calculating these periods? And the answer was because we could count points that way. You know, Philip is the one who started the whole process of relating those periods to things in physics, back in the old days when he was a physicist. And in those days, I was a mathematician. And now I give a different answer to why we'd be interested in those periods, because of the connection to string theory. So I think I have the role here of being the most physical of the speakers in this number theory and physics conference, at least by subject matter, if not by training. And I'm going to talk about where this comes from a little bit in string theory. So string theorists discovered many years ago that string theories can be naturally formulated in 10-dimensional spacetimes. That's supersymmetric string theories. There are some variants on this. There are the bosonic string theories in 26 dimensions. There is M theory, which is a more recent development, which lives in 11 dimensions. But the basic picture of string theory happens in 10-dimensional spacetimes. And in order to relate a theory, physical theory in 10 spacetime dimensions to the 4-dimensional world that we see around us, the traditional thing to do has been to consider spacetimes of the form a 6-dimensional compact Riemannian manifold crossed with Minkowski space in 3 + 1 dimensions. So because of notational difficulties I'm about to have in a few minutes, I'll just call that M4, but it's to be thought of as Minkowski space in 4 dimensions. And then you can hope to relate properties of the 4-dimensional theory, the physical properties of the 4-dimensional theory, to properties that would be calculated out of the physics on the compact 6-dimensional manifold. And in particular, many of those properties are quite geometric in nature. So there's a relationship, close relationship to differential and algebraic geometry in trying to study 4-dimensional physical theories from this point of view. So what 6-dimensional manifolds are we supposed to take? Well, if you want to preserve supersymmetry, and I'll write supersymmetry, the whole word right now, and then I'll tell you that because of writing on blackboards and transparencies, people like to abbreviate it SUSY. So we want supersymmetry in the 4-dimensional theory. You can ask whether we really want that, but that's a topic for a physics lecture, not a math lecture. So the physicists want supersymmetry in the 4-dimensional theory, and in order to get that, they need a covariantly constant spinor on the 6-dimensional space. Analyzing that problem of which compact Riemannian manifolds have covariantly constant spinors leads you to the theory of holonomy groups. The holonomy of that Riemannian metric is restricted, and it can take only one of a few values. And just to briefly summarize the results, you end up discovering that for a 6-dimensional manifold with, say, minimal supersymmetry, you want a Ricci flat Kähler metric, and that ends up implying that X6 is actually an algebraic variety, projective algebraic variety. So there's this amazing connection between algebraic geometry and differential geometry when you think about the metric on this space, and this attempt to compactify 10-dimensional string theory down to a 4-dimensional, what physicists call an effective theory in 4 dimensions. Well, the way that physicists then study that 4-dimensional theory is by formulating a theory of strings. So I imagine the string kind of moving along in time and sweeping out what's...
Does the total space need to split?
Okay, so there are many variants on this problem. The total space might not split, right? I've written down a total space which is metrically split. That's not necessary. There are other solutions which look like topological products but not metric products, and they end up requiring not covariantly constant spinors, but spinors whose covariant derivative is some specific tensor that's somehow related to a bit of extra geometry that comes in the situation, and that leads to some different problems in geometry. So this is not the only possible class of solutions you might look at. And I guess the other comment to be made in a physics talk is that we've learned pretty conclusively in the last few years that the global structure of the universe we live in is not Minkowskian, but is a universe with a positive cosmological constant. And so one would like to make string theory models with a positive cosmological constant. Turns out to be, so this is zero, cosmological constant 0. Turns out to be easy to make them with negative cosmological constant and very hard to make them with positive cosmological constant. So as a description of the actual cosmological world we live in, there are a lot of questions these days about this approach.
From the restriction on the holonomy,
Yes.
so when you say which is what kilometer, you're saying that implies that there is a complex structure and a metric.
Yeah, in fact, there's a complete classification of holonomy for Riemannian metrics, holonomy groups for Riemannian metrics, and it follows from that classification that the holonomy that we're looking at here is actually SU3, and that implies these properties I mentioned.
And how do you get from that to predict the boundary?
So with holonomy SU3, H20 has to vanish on this Kähler manifold. That makes H11 all algebraic, and because it's Kähler, you end up getting a Hodge metric and an embedding into projective space.
Are we going to need to know what a spinor is and holonomy and
So let me tell you what I'm going to do in these lectures. What I'm going to do in these lectures is briefly skim the surface of some physics and tell you some words and some formulations and things of that sort without explaining in too much detail the physics. And then I'll make connection to some detailed calculation in mathematics, and we'll focus our attention on the detailed calculation in mathematics. But that won't be a sort of continuous process. We'll keep sort of riding back up to the surface, thinking a little bit more about the physics, seeing a different calculation that's related in mathematics. So yes and no is the answer. If you knew what a spinor was, it'd be great. But you won't really need to know that to absorb what's going to happen in the future. All right. So how do physicists study this kind of theory? Well, they imagine the string sweeping out in time what's called a world sheet. So that's some surface, typically called sigma. And they imagine this propagating string somehow happening inside of X, inside of the 6-manifold X6. And so this becomes a physical theory that's based on maps from world sheets into X6 somehow. And those world sheets, at least in the initial formulation of the theory, those world sheets should be taken with Lorentz signature. So we should think about metrics on surfaces that have signature 1, 1. And then we'd like to formulate the physics of a theory of maps like this. And although string theory itself is a more complicated physical theory, the ingredients to string theory come from studying the quantum field theories based on those maps. So this is a pretty standard kind of physical theory to describe. It's a two-dimensional quantum field theory, 1 plus 1 dimensional quantum field theory, and it's a theory of quantum fields where the field essentially means a map from a Riemann surface, a Lorentz signature surface into a compact Riemannian manifold. And there are various details about how you formulate a theory, which I'm not going to describe right at the moment. The analysis of those quantum field theories is what led directly to these remarkable results about Calabi-Yau manifolds, about the 6-dimensional manifolds with holonomy SU3. This collection of results called mirror symmetry, and led to these very remarkable predictions that certain calculations you could make on one of these Calabi-Yau manifolds, and I'll try to describe in some intuitive fashion the type of calculation that's made, could be related to different kinds of calculations on different Calabi-Yau manifolds. And when this was first proposed, it was kind of scoffed at by mathematicians, most mathematicians who heard about it. At the time, I knew not so much physics and quite a bit about Calabi-Yau manifolds, and I thought it was ridiculous. But it's true. I mean, it's not only an outrageous proposal, but it happens to be true, and we've come to some degree of understanding the mathematical content of that statement in the intervening years. So that, again, that dates from the early 90s. The kind of calculation which is made in this quantum field theory is an expansion in some parameter, and when you do this expansion in some parameter that's usually called Q, number theorists know about Q, and it's a similar Q, you do an expansion in some parameter called Q, and the coefficients are somehow instanton numbers, or numbers of instantons. And the way that you try to address these instanton numbers is you look at, so you want all maps in a fixed cohomology class of maps with minimum energy. So we have to define minimum action, I should say. So we have to define the action, which is one of the key ingredients to specifying the physical theory. But if you can figure out how many maps have minimal action, and if you set things up right, maybe there will be a finite number that have minimum action. So you can call that the number of maps with action associated to some cohomology class D, and then you make some kind of series which looks like a number of maps times an expansion parameter raised to the D. That's a multi-index and Q. There are actually a number of Qs in there. That maybe with some initial value that didn't have anything to do with the number of maps in cohomology classes, some n0, that's some kind of physical quantity in this theory. And this is the way to start trying to calculate the physical quantity, to calculate it in terms of an expansion like this. Now, these calculations are motivated by Feynman diagrams. They're analogs of Feynman diagrams in this context. The expansions that we make are not necessarily known to be convergent, not even necessarily expected to be convergent, but in the cases that we'll look at here, the expansions really will be convergent, so that won't be an issue. And the physical quantity which had this kind of instanton expansion, so the story of mirror symmetry was that this physical quantity which had this kind of instanton expansion for one of the Calabi-Yau manifolds, when you looked at the so-called mirror partner Calabi-Yau manifold, all of the instanton contributions vanished and only this n0 mattered. So it was pretty easy to calculate what the answer was in that case. You didn't have to worry about maps from Riemann surfaces having a fixed cohomology class and counting how many satisfied some property. You could just get away with making this first term calculation, and then that got related by mirror symmetry. So a sort of typical sort of thing, e.g., ND could be the so-called Gromov-Witten invariance of the Calabi-Yau manifold X, counting the numbers of rational curves of fixed degree or fixed cohomology class, and making an appropriate series like this out of the Gromov-Witten invariance yields a physical quantity which could be calculated using periods, could be calculated on a different Calabi-Yau manifold using its periods. That was kind of the beginning story of mirror symmetry. Now, those instanton calculations are pretty hard. As geometric, one of the reasons why this was so striking was that at the time that Candelas and his collaborators made those first calculations, only the first few Gromov-Witten invariants for a simple example of a Calabi-Yau manifold, I should have given you this already. So one example of a Calabi-Yau manifold is given by a hypersurface in CP4. Well, I'm mixing numbers here. That's a complex dimension. That's a real dimension. Where X is given by, say, the zeros of some simple-looking polynomial, degree 5, in CP4. That's an example of a Calabi-Yau manifold. And the numbers of rational curves for that family of Calabi-Yau manifolds were known for degrees 1 and 2, and just right at the moment that Candelas and company were making their prediction, a calculation was made for degree 3, but it was very hard. And on the other hand, by this sort of miraculous method, these guys produced a nice generating function, and they could just read off coefficients as far as they wanted to. And when all of the details were sorted out, it turned out that their predictions agreed precisely with the numbers that mathematicians were able to calculate. And later, those predicted numbers were proved to be the correct numbers evaluating Gromov-Witten invariance. So it was a very pleasant story, but involved a lot of pretty technical mathematics in getting your hands on those Gromov-Witten invariants. So the theme of these lectures is going to be an alternative way of addressing the quantum field theories associated to this manifold X. And for certain X's, so I'm going to say can sometimes be described by a much simpler physical model, which is called a gauged linear sigma model. That's just a name. And if you use this gauged linear sigma model approach, it turns out that the instantons are easy to calculate. Well, at least straightforward to calculate. There aren't complicated computations to be done in moduli spaces. Essentially what you have to do in the other situation is work in components in the Hilbert scheme in some projective space of a sort of hard to control behavior, and you have to worry about the singularities in those components of the Hilbert scheme to make sure you get the instanton contributions calculated correctly. In this case, all those complications go away. The instantons are easy to calculate. And so you then need to ask why these gauged linear sigma models are related to the actual quantum field theories that we're interested in. So these are related to the original quantum field theories by a process called renormalization in physics. And the effect of renormalization in this context implies that if I want to calculate a physical quantity, such as that instanton expansion that I had on the previous page, something like this sum of md q to the d, if I want to calculate a physical quantity like that, you need a coordinate change, you need a parameter change in the q's when comparing answers. So the answers that I get will be very easy to calculate. They'll be the wrong answers because when you formally expand in Q in the problem that I'll study, you'll get different numbers than the Gromov-Witten invariance. On the other hand, there is a well-defined change of coordinates which can actually be calculated easily using the periods, which has the property that if you make that change of coordinates, you get the original Gromov-Witten invariance. There's not a direct mathematical proof of that fact. That's an expectation from physics, and it's something which is a consequence of the mirror theorem that I mentioned, the Giventhal, Liang, Liu, Yao mirror theorem that I mentioned earlier that establishes the validity of this calculational approach. Okay, so that's sort of the plan. And in order to do it, I have to tell you about gauged linear sigma models. And the most efficient way to explain gauged linear sigma models to you is to use what's called a superspace formulation. So I have to introduce superspace. And this is one of these places where I'm not exactly going to tell you to go to sleep and wake up in a few minutes, but I am going to say that if you miss some of the details in my discussion of superspace, it won't hurt you that much later on. Let me just give the reference for some of the supersymmetric theories that I'm going to briefly sketch. So there's a long thing called supersolutions, which is in Quantum Fields and Strings, which is a volume 1. Supersolutions is by Deligne and Fried. So P. Deligne and Dan Fried, and the book is edited by Deligne et al. There are 7 or 8 of us, I can't even remember anymore, and it's AMS 1998 maybe, something like that. So there was a special year at IAS in 96, 97, and at one point in the spring semester, Ed Witten gave us all some super homework, which was homework about supersymmetric stuff. And the solutions to this homework generated a 150-page manuscript by Deligne and Fried, which became part of the book that we published afterwards. So it's got a very clear and much more detailed version of what I'm about to briefly sketch for you with superspace and supermanifolds. The problem is that these supersymmetric theories involve lots of complicated-looking fields, and if you start to do what a physicist naturally does, which is to write down the action, as I mentioned before, the action is the key quantity. If you just write down the action for this theory, it's very hard to keep track of all of the pieces of the thing. But if you introduce this formalism of superspace, you can keep track of the pieces quite nicely. So superspace, a superspace is a supermanifold. It's a supermanifold, of course, many of you won't really know what supermanifolds are, whose quote-unquote body is Minkowski space. So what's a supermanifold? Well, supermanifolds, super anything, sometimes called Z2 graded anything, is this series of interesting constructions where you put a Z2 grading on things, and the even label graded object is usually the typical object. So on a manifold, we have ordinary vector fields, which are thought of in this language as even vector fields. And then we also have things called odd vector fields, whose sign properties in things like Lie derivatives are opposite of what ordinary vector fields have as sign properties. So to think of a supermanifold, you have to basically think of an ordinary manifold, that's the body, and it has ordinary coordinates and ordinary vector fields on it. And then you have some kind of bundle over that manifold, which is a bundle with Grassmann coordinates in it, anti-commuting coordinates in it, which represents the odd graded part of the Z2 graded structure on the tangent space. There are lots of structures that you can discuss, and I don't want to get into too many details, but the particular superspace that I'm interested in is based on the Minkowski space M2. So as I mentioned, we need to study two-dimensional theories, and it's got a certain amount of supersymmetry, and that gets labeled in this particular context with the label 2, 2, so it's what's called n equal 2, 2 supersymmetry in 2 dimensions. And to describe it, I should introduce coordinates x0 and x1. So these are ordinary coordinates on Minkowski space, constructed so that the Lorentz signature metric is diagonal in this form. Then I want to introduce vector fields d plus or minus, which look like the vector fields in the 0 and 1 directions, but the sum and difference of those vector fields. It turns out to be convenient to formulate the theory in those terms. So these are even vector fields, even in this Z2 graded sense. So here everything is Z2 graded. These are even vector fields. And now I have some odd vector fields, which I think of as, so this supermanifold that I'm writing down is the supermanifold that I'm writing down is ordinary Minkowski space equipped with this extra structure. And the odd vector fields, they're complex valued, and I write them as d plus, d minus, d plus bar, and d minus bar. And then there's some commutation relations. So lots of the commutators are 0. I'll just write some sample ones that are 0. So d plus is 0, d minus is 0. Lots of other ones are 0. But the ones that are non-zero, d plus with d plus bar gives me minus 2 times the even vector field. The bracket of two odd things is even. And the d minus bar is minus 2 times the odd vector field, del minus. So that's the basic algebraic structure that we add to the ordinary vector fields that we would see on a Minkowski space. So how is that used to write down a physical theory? Well, I consider a super Lie algebra, which is the extension of the Poincare algebra, that's the natural symmetry algebra of Minkowski space, by these odd vector fields. And this space M2, 2, 2 is acted upon by the exponential, let me call that script L, the exponential of script L. So that's a supergroup, and to define a supergroup, you have to think a little bit about what to do with the even and odd structures, but the usual exponential map is used on the even part, and then the odd part defines some structure on the tangent space. And this superspace is a homogeneous space, in fact, for that action. And these d plus, the d plus and the round d plus and so on are left invariant vector fields on the superspace M2, 2, 2. So the typical sort of thing that you want to do in writing down a physical theory, well, I've already described, for example, that if I had the Calabi-Yau manifold, I might be wanting to do maps to the Calabi-Yau manifold. Here, I'm going to take maps from my superspace to some target, and the target is going to be Cn for these gauged linear sigma models. So I'm going to think of that as a map phi. And the way you're supposed to interpret this kind of map, well, that contains a lot of data because of the extra odd generators. However, you can do things like take derivatives of the map, and then you can restrict those derivatives to the so-called body, to the Minkowski space part of the theory. And this produces various fields, usual fields that a field theory in physics would have had. So field theories in physics, you could have a complex vector space valued field. Capital phi itself, restricted to the manifold, will be something that we call little phi. That's just a map from Minkowski space to, it's just a Cn valued function on Minkowski space. But because of these derivatives, so the anti-commuting property means that you don't actually get to put in the same derivative more than once. So we have a maximum of 4 here, d plus, d minus, d plus bar, and d minus bar. And by taking various combinations of those, you can extract the different components of this thing which is called a superfield. Should have mentioned that. And we'll try to study physical theories based on superfields like that. Now, I mentioned that this is a compact way of formulating a physical theory. To study this physical theory in more detail, you actually need to work on arbitrary Riemann surfaces, for example, or arbitrary Lorentz signature surfaces. And when you do that, you should actually write things out in terms of these usual fields. So this is, in a way, a shorthand. The superspace formalism is a shorthand for a much more complicated theory, and it's a shorthand which has the advantage that you can verify the supersymmetry property. Supersymmetry means that there is going to be an action of this super Poincare algebra, the extension of the Poincare algebra, on the physical theory, which preserves everything, and that can easily be verified if you're able to give this kind of superspace formulation for the theory. Okay, so the ingredients for my theory are going to be this chiral superfield. It's a superfield which has to have one other property. It's got to be a so-called chiral superfield. So the gauge linear sigma model has a chiral superfield, and chiral superfield means that d plus bar phi I and d minus bar phi I are both 0. So it's some kind of holomorphic function of coordinates in these variables. I'll put that in quotes because those were odd vector fields, not even vector fields. So I use this chiral superfield, and I'm also going to use a group action. So I'm also going to need a compact abelian Lie group, compact abelian group G, and an action, a representation of G into, well, it's really into U1 to the N as a subgroup, if you like, of GL and C. So I've got a way of acting on Cn, but I'm going to make sure that it's consistent with some particular coordinates that I'm choosing. The phi I, were the components of the capital phi. I guess since I'm listing all the data here, I'll just mention one other piece of data which we'll need. We will also need to choose an element tau in the homomorphisms of the Lie algebra into the complex numbers, and we'll need to choose W, which is a G-invariant polynomial on Cn. Those are going to be the basic ingredients for describing this thing called a gauged linear sigma model. So very simple looking stuff, and as we'll see, the kind of calculations that have to be made are, once you've interpreted the physics a little bit, are fairly straightforward where some of this stuff is concerned. Well, now, as in any physical theory, I need to write an action for this thing, a Lagrangian density. And the Lagrangian density that you start out with, well, first of all, I'm going to write it in terms of superspace integrals. So if you know anything about supermanifold theory, this will look familiar. If not, essentially, this d4 theta, which means d plus theta, d theta plus, d theta minus, d theta plus bar, d theta minus bar, that's what d4 theta stands for. It's an integral with respect to these fermionic variables. And since I've got left invariant vector fields, you could easily imagine somehow inverting that with an integral. What's unusual is the properties of this integral, called the Berezinian, And if you know about those, that's great, and if you don't, that's fine too. But because of the odd variable part, when I do these fermionic integrals, this d4 theta is sort of the maximum thing I might possibly do. And what I'll take is a component-wise exponential of the e to the minus I times the derivative of this representation. Rho was the representation mapping the group to u1 to the n, composed with v. I forgot to tell you what v was. Sorry about that. Composed with v squared, and then traditionally in physics you put in a so-called coupling constant, 1 over 4 e squared. That e is, this e is an exponential and that e is a constant. Sorry about that. That's physics notation. Norm sigma squared. So I forgot to tell you what z is, but that's the basic term in the Lagrangian, and those are called kinetic terms for the fields. It's gauge invariant, G invariant kinetic terms. And that just makes sure that the G action preserves the Lagrangian, whatever that means. So V here is a so-called gauge multiplet. And it's a map from my superspace to the Lie algebra of the compact group. And sigma is, let me get the right derivative here. Oops. Sigma is d plus bar d minus of v. And sigma has a slightly different property than chiral. Sigma is twisted chiral, which means that d plus bar sigma and d minus sigma are both 0, which follows directly from the way that sigma was defined. So sigma is like the curvature of the gauge field. It's got two derivatives in it. It's not quite the curvature because these are odd derivatives, but it's close. It's the thing which naturally goes into the Lagrangian in a gauge theory, and this is the simplest possible Lagrangian you could possibly write down.
What's the norm?
Sorry. So this is so d rho composed with v takes values in Cn. I component-wise exponentiate it, and then it's the usual complex norm. Well, sorry. It's a superspace version of the usual complex norm. Let me just say that. Sorry, no, I'm not in supermanifolds by that point, right? I'm in Cn, so it's just the usual norm in Cn. And same thing for sigma. Well, let's see. I guess I need a norm, so I need a norm on G in order to define this term here, the sigma squared. Well, that's not quite the most general possible Lagrangian that you can write down with all the symmetries in the problem. And it's a general feature of quantum field theories that you need to include all terms in the Lagrangian which have the symmetries of the problem because of this renormalization phenomenon. So in renormalization, you try to study the behavior of the quantum field theory as you change a certain approximation to it, how the parameters that go into the Lagrangian depend on certain parameters in that approximation. So in order to be able to do that effectively, you're sort of always required to put in the maximal set of terms that you can imagine that would be relevant to the theory. And in the particular case that we're studying, there are two other terms that can be put in. So it's this kinetic term that I had on the previous page, plus two other terms. One of them is the real part of an integral now just of two of the superspace variables of this holomorphic function applied to these superfields. And the other is the imaginary part of two different superspace variables of the a natural pairing. This is the pairing of dual spaces of tau with sigma. Tau, if you may recall a moment ago, was a Hom GC valued guy. So that gives me some complex number, and I can put in these two kinds of terms, natural terms, into this thing. And that simple-looking physical system is what's called the gauge linear sigma model. So just to summarize again, the ingredients were W, which was this polynomial, the group G with its action rho onto u to the n. And of course, the coefficients of w will be parameters, and tau, essentially, this choice of tau provides additional parameters in this particular theory. So by the end of today, I will explain to you what these have to do with Calabi-Yau manifolds. We'll see in an example very explicitly what they had to do with Calabi-Yau manifolds. But at least for a moment, we can just kind of look at these. Actually, let me skip ahead one step and go ahead and do that. So here's an example of a type of thing that we might look at. So a fairly typical example, I'm going to take as my polynomial. So this is going to be a polynomial in 6 variables. And my polynomial is going to be x0, x1 to the 5th, up through x0, x5 to the 5th, plus x0, x1, x2, x3, x4, x5. And if you wanted to put coefficients in there, you'd be welcome to do so. The u1, the group is going to be u1, and the action on c to the 6th here, well, to tell you what the action is, I have to tell you essentially what characters of u1 the various variables are going to be acted upon by. And so I'll just tell you that x0, x1 up to x5, the characters can be characterized by the exponent that you need to put on a generator. So those exponents are -5, 1, 1, 1, and 1, and that specifies the action. So what I really mean is to take a thing t there and send this guy to t to the -5 x0, t x1, and so on. That's what this notation means, to specify the group action. So there's a very concrete looking example, and well, it's not an accident that it's some kind of cousin of the quintic that I mentioned before, and we'll see exactly how it's related to the quintic in just a few minutes. Okay, so there's a feature of these things which can also be encoded in the combinatorics, which is whether or not you're expecting an interesting interacting theory in the infrared limit. That's the physics term. And I'll come back to that in just a second. What I want to do is what's called the low energy analysis of this model. And so I have to say one thing that's, again, related to superspace, and then, but after that it will become sort of more standard geometry. So to make life simple, let's pick a basis for the Lie algebra, and then we can write V in components, V1 up to V something or other, n minus d, I think is what I like to call it. And then we can describe the group action by sending phi I, well, by saying that the generator e to the VA takes phi I to a certain e to the VA raised to the Q IA power times phi I, something like that, so that these, the numbers that I had down here explicitly, in this column, are being described now as two index guys, QIA, in this explicit kind of notation. And in the low energy analysis, what you do in many of these superspace theories is you notice that the derivatives of certain fields, certain of these component fields, do not occur in the action. And so what you're trying to do classically is minimize the action, and you can solve for these fields. And if you expand tau as IR plus 1 over 2 pi theta, that's the conventional, I don't know why, conventional expansion of tau, then you discover that there are fields dA, which is a component of VA, which when you solve in this way turns out to be, it's got a coupling constant in it, and then it's the sum of QIA norm phi I squared minus R A. And there's a similar field, this is a component of phi I, which you can solve for explicitly as being minus the partial derivative of the polynomial function with respect to the ith variable. So these are two very explicit things that you can do, and having done them, it turns out that the potential for what physicists call bosonic fields in this theory is 1 over 2e squared times the sum of the dA squared plus the sum of norm fi squared plus another term which I'm going to suppress for now, and I'll come back and tell you what it is probably next time when we need it. So this is a straightforward manipulation. If you've studied Lagrangian mechanics, like if you took 2 years of mechanics as an undergraduate, you might have studied Lagrangian mechanics. This kind of solving for fields whose derivatives don't appear in the Lagrangian is pretty straightforward. And from the action that I wrote down, and maybe the techniques that are mentioned in the book that I gave a reference for, you can pretty easily work out that this is the correct thing. Now, in the classical analysis of the theory, what you'd like to do is to make the potential minimum a minimum, and it's pretty clear that in order to make that potential a minimum, so to minimize the potential, I've got to make those two quadratic terms vanish. Those were real quantities. So to minimize u,
Excuse me,
yes,
can we leave the end of that?
yes, I'd be happy to. Okay, so I'll try to do this for a minute. So to minimize u, must have dA equals 0 and fi equals 0. So now we get to something which is really very geometric in nature. Let me go back to my example just briefly. In my example, this dA looks like, it looks like minus 5 0 squared plus phi 1 squared up to phi 5 squared minus r. There's just one r in this case. And that's supposed to be 0. And then I'm also supposed to take the partial of w with respect to the various variables to be equal to 0. Now, w by construction is x0 times a quintic polynomial in the other 5 variables. And so the partial of w with respect to x0 turns out to be this quintic polynomial. Partial of w with respect to the xi turns out to be x0 times the partial of the quintic with respect to the xi. And all of these are supposed to vanish. I'm writing down a classical analysis of this quantum theory, and what we're about to see is that the set of classical vacua, so-called, is very closely related to a Calabi-Yau manifold, and that's one of the arguments that exist in the physics literature for why the endpoint of renormalization, whether you started with what's called sigma model whose target is the Calabi-Yau manifold, the one I was talking about at the beginning of the hour, or when you start with this simpler to formulate gauged linear sigma model, they should be the same physical theory. But because of that renormalization process, there may be some changes of parameters within the physics that you see along the way. So in my example here, if I set all these things equal to 0, well, the result that I get differs depending on the sign of r. So let me take r to be, so if r is negative, then not all of phi 1 up to phi 5 can vanish. And that's starting, if you know about geometric constructions for projective space, that's starting to look kind of familiar. In fact, in this situation, I'll have C5 minus the origin. When I look at possible values for phi 1 to phi 5, inside C5 minus the origin, well, I've got so I'm sort of ignoring the phi 0 at the moment, so I've still got the phi 0. Inside there I've got C cross. Once I've fixed the value of phi 0, this is not quite cross, but it's, anyway, it's not quite cross. Once I've fixed the value of phi 0, I've got a 9-sphere for each value of phi 0. It's some bundle, right? I've got a 9-sphere, and now the U1 action is purely on that 9-sphere, but there's some twisting on the C. So you mod out by the U1. I forgot to tell you, this is a gauge theory. If you've ever heard anything about gauge theories, you know that the physical interpretation of the gauge theory, you've written down a gauge invariant action, and now you're supposed to look at physical states, which also the set of physical states has to be invariant under this gauge group, and you have to mod out by the gauge equivalence on physical states to end up with the sort of final answer. So I get to mod out by my group at the end. And if I didn't have this phi 0 there, and that certainly would have been an example I could have studied of the gauge linear sigma model, I would have just gotten this picture S9 mod U1 using this representation of the sphere. And of course, when I say R negative, I probably mean R positive if I really want a sphere. Well, I'm confused. But anyway, I'd get CP4. If I were able to sort out the confusion, I would get CP4. And this extra phi 0 actually gives me a complex line bundle. And if you work out what it is, it's the total space of the complex line bundle O minus 5 over CP4 in this particular example. So phi 0 represents the fiber coordinate. Phi 1 up through phi 5 represent the homogeneous coordinates on the projective space, and the fact that they're tied together by this group action is what actually makes it be a non-trivial bundle structure in this particular setup. I'm also supposed to be imposing these conditions, that the partial derivatives of W with respect to the variables vanish. And if I impose those conditions, well, if W is generic, so if W is generic, and in particular has a property that algebraic geometers would call transverse, W and its partials with respect to the various variables, if P is generic, then P and its partials with respect to the various variables will share no common zero outside of the origin. On the other hand, the origin is not part of my theory here. So the origin was left out, and so that's the origin in C5, right? So if the origin is left out, those can't all share a common zero, and the only option is that in order to satisfy these equations over here, the only option is that x0 has to vanish. So P will have to vanish, and x0 will have to vanish, and although I had the x0 in there in order to sort of see a fiber coordinate on this bundle O minus 5, this second step set me to x0 equals 0. So imposing that condition really now puts me down into CP4, and then this is the equation of a quintic. So imposing that condition gives me a quintic hypersurface in CP4. So that's the Calabi-Yau that we started with as an example. So here's a situation in which we take some rather abstract-looking data. Well, there's a condition on the data which I have to tell you, but we wrote down a polynomial and a group action and just a linear space, and we ended up through this low-energy analysis of a physical theory creating a hypersurface in an ambient space. Variants, or rather special cases of this actually will produce complete intersections in toric varieties quite arbitrarily as possible Calabi-Yau manifolds, and any complete intersection in a toric variety can be realized through this gauge linear sigma model construction, where we get a simpler handle on the physics involved in this business. And again, due to physical arguments, we expect whatever physics calculations we make in this gauge linear sigma model will differ only by a parameter change, a change of q coordinate, from the actual Gromov-Witten invariant type of calculation that you would make directly on the Calabi-Yau manifold. So let me mention what the other constraint is that I alluded to. So there's a constraint on the choices. So remember, the basic data that we're working with is some compact abelian group of representation and a polynomial W. And the so the first thing to say is that we want to be able to vary parameters here, and so we should consider the family of all theories of this kind with the coefficients varying in this polynomial. So the real data that we want is the set of monomials appearing in W, right? It's that set which is going to determine the family of theories. And remember that I also mentioned this tau, which is another set of parameters essentially determined by the choice of group. So there are basically two parameters that have to be, two kinds of parameters that have to be thought about in this family of theories. So how do I characterize a set of monomials? Well, one possible way is to write the monomials out. Some monomial can be written out as, I want to get the notation. Sorry, I don't know what page my notation is on for this. Okay, well, let me just pull it out of here. So I want to write the monomial as a product of powers of x so let's make that TAI, and I'll call that TA. And I think of TA is the row of a matrix T, a non-negative integer matrix T. So that's one way of specifying the set of monomials. On the other hand, if I look at the group G, so G has a set of, or determines, I should say, a set of G invariant Laurent monomials. And in fact, G itself can be determined by the set of G invariant Laurent monomials. So that's some other matrix. Yeah, cleverly, that was supposed to be T. Sorry about that. So this was supposed to be P. Oh, doesn't matter. So these would have been TRs, TRI. And then I could make some other matrix P, which will really confuse me. So P has rows PAI, where x to the PA is the product of xi to the PAI. So these are integers now, not necessarily non-negative, and they're determining by the subset G of U1 to the n determines a subgroup of U1 to the n can be determined by its set of invariant monomials and vice versa. So I'm just looking for a basis of the invariant monomials, and I write down that basis. And now, since the monomials in...
Dave, could you slide up?
Yeah, sorry. So I might have neglected to say that W was supposed to be G invariant. Did I say that? I don't remember. W is supposed to be G invariant. That was a key thing from the beginning. And since W is G invariant, can I slide it up and slide it down? There we go. So since W is G invariant, each of the monomials that appeared in W can be written as a product of powers of the monomials that appear in P, right? So what that means is that T can be written in some factored form as S times P, where this expresses the way of writing the monomials appearing in W in terms of a fundamental set of monomials. So we have some non-negative integer matrix, and maybe it has rank D, something like that, D being the rank of the group, and then we have some way of factoring that matrix into S times P, and that really captures all of the data, essentially, that we have in this problem, because you can recover G by knowing P, and the S, I mean, the fact that it had to factor was sort of part of the data. Well, it turns out that for cases where I get a Calabi-Yau theory, and I'll come to the condition for that, well, I won't come to the condition for that, so I'll just say it quickly in a second. For cases where I get a Calabi-Yau theory, the mirror theory is determined by a factorization of the transpose. My time is up, determined by a factorization of the transpose. So we have the transpose of T factored as the transpose of P times the transpose of S. So the new monomials, in this case, are determined by a new group, which has to do with the S matrix from before. And this is what the prediction, this is a perhaps unrecognizable generalization of construction first formulated by Batarev in the early 90s to explain how to work out mirrors of hypersurfaces in toric varieties. This is a generalization which Batarev and Borisov did to complete intersections. It's just a slightly different combinatorial way of formulating that distinction. So let me quickly mention what the condition is for what's called a conformally invariant theory. To get a conformally invariant theory in the infrared, which means after renormalization, there's a condition, and that's the condition that we'll stick with in order to guarantee that we're going to get Calabi-Yau type theories. So there's supposed to exist rational vectors, mu and nu, which are rational vectors, such that T times mu is 1, 1, 1 transpose, and nu transpose times T is equal to 1, 1, 1. Whatever the sizes of these matrices are. So for the physicists in the room, what I'm looking at is a chiral R symmetry, which will become the expected R symmetry in the infrared, and I'm demanding that that exists in the ultraviolet formulation of the theory if I'm expecting an interesting interacting theory in the infrared. So that condition is satisfied by the example